really where the rubber meets the road in terms of learning reactions. Hi, Chemistry 3101. This is Chapter 7 that deals with alkyl halides and nucleophilic substitution and elimination reactions. A big chapter, lots of interesting things to learn in this chapter. And let's start out by defining what an alkyl halide is, because for some reason we need an alkyl halide to do all of these reactions. All right, let's take a look here. It says alkyl halides undergo substitution and elimination reactions. Okay, that's fine. If you take a look at these compounds here, you see that X is attached to a carbon in all three of these. And in organic chemistry, whenever you see X, X means 3 out of the 4 halogens: chlorine, bromine, and iodine. Why not fluorine? It's because fluorine is not a good leaving group. And that's something that we discussed a little bit in Chapter 6, and we're going to discuss even more in this chapter. Now, if we look at the hybridization of each one of these carbons, you can kind of see that one of them is different than everything else. Right? We see that this one has a carbon that's sp3 hybridized, whereas the other two have sp2 hybridization. So we would not refer to these two as alkyl halides, right? We would refer to this one as an aryl halide. So this would be an aryl halide because the halogen is attached to an aromatic ring. And we would refer to this one as a vinyl halide because the halogen is attached to a vinyl group. The alkyl halide is the one where the halogen is attached to the alkyl group. And so this one would be our alkyl halide. Thus, we're going to be spending time focusing on compounds where we have a halogen attached to an sp3 hybridized carbon. We're going to talk about aryl halides and vinyl halides, but that's in another chapter towards the end of the course. Well, now that we've defined what an alkyl halide is, let's talk a little bit about what substitution and elimination reactions are. And this is going to be a huge focus of this chapter. And we have our alkyl halides, okay. And it says here that they can undergo substitution reactions when they're reacted with a nucleophile. So let's take a look here. We've got an alkyl halide. Remember the X could represent iodide, bromide, or chloride, either one. And then we treat it with some kind of nucleophile, and you see that we have the halogen acting as a leaving group because it's gone. And we see that the nucleophile was doing what it does. It was, performing a nucleophilic attack. You could even try drawing the curved arrows for this, and you'd see that you have the nucleophilic attack occurring and the loss of leaving group occurring simultaneously. Again, this arrow represents the nucleophilic attack, and this one represents the loss of leaving group. And we're going to talk about that a lot this class. So that's a substitution reaction. We substituted the halogen, the X, for a nucleophile. Substitution. Alkyl halides can also undergo what's called an elimination reaction when you treat them with a base. So let's see what's going on here is that we're doing an elimination. We're eliminating something from the alkyl halide. And now we're ending up with a double bond. So we're making an alkene. That's kind of interesting. And what did we eliminate from the molecule? Well, the base, we didn't eliminate that because that was never part of the molecule. What we eliminated was a hydrogen atom and a halogen. So we lost H and X from the molecule. Now we could draw a mechanism for that as well, and we will, but I'm going to do that in a little bit. So what do nucleophiles and bases have in common? That's something that we want to think about. It says that when a reagent can react as a nucleophile or a base, then we can get a competition between substitution and elimination, right? Just think about hydroxide. Sodium hydroxide is composed of sodium plus and hydroxide, which is OH minus. Well, OH minus, if it's negative, it can certainly react with an electrophile, so it's a nucleophile. And you all passed general chemistry too, so I'm sure you saw about 1,000 times that sodium hydroxide is a strong base. Therefore, hydroxide, again, is both a nucleophile and a base. Well, if substitution occurs with a nucleophile, that means that hydroxide can behave as a nucleophile. And that's what we see here. We see the product of nucleophilic attack is this substitution product. Whereas we can also get elimination where we lose a hydrogen atom and the chlorine to form this alkene. It says here in this example shown here, which compound is the substrate? You're going to hear me use the word substrate pretty often, probably. If you've studied biology and you've studied enzymatic reactions, you've probably heard of an enzyme substrate complex or something like that. Substrate in organic chemistry really is just referring to the starting material. Starting material, or the reactant. Therefore, this would be our substrate, okay? This compound is called isopropyl chloride or 2-chloropropane, either way. But we've got an elimination product formed, and we've got a substitution product formed. You can see that we end up with a mixture. The elimination product is the major product, and the substitution product is the minor product. So we get a couple of things, and this is where chemistry gets really interesting. When we have to say, okay, well, I'm reacting these two things, sodium hydroxide and this alkyl halide, and now I'm not just going to make one product, but I'm going to make two different products. Wow, that's interesting. Okay, well, let's dig in a little deeper on this whole substitution and elimination thing. Follow along with me here. It says 2 main reasons why alkyl halides undergo substitution and elimination reactions. Like, why do these things even happen? Okay, well, let's take a look. Number 1, if we look at our substrate that's got a halogen on it, we know the halogens are electronegative, so they're electron withdrawing, and that creates a partial positive charge. Right, we looked at this example the other day when we were talking about nucleophiles and electrophiles, and we had methyl chloride. I'll just draw it here for you quickly. We had methyl chloride. We even looked at the electrostatic potential map, and we said, well, chlorine is pulling electron density towards itself, and that renders the carbon partially positive. So when it's partially positive, it makes it susceptible to nucleophilic attack, right? Opposites attract. Something else that I want to point out is that the carbon that the halogen is attached to, that's called an alpha carbon. So this carbon here, any carbon attached directly to a halogen is called an alpha carbon. And you can imagine the carbon that's attached to the alpha would be called the beta, then the gamma, so on and so forth. Anyhow, so yeah, we have a halogen. It pulls electron density away from the carbon, thus rendering it electrophilic. It's susceptible to nucleophilic attack. That's the first point. And the second point is that the halogen acts as a leaving group, right? We know that the halogens, chloride, bromide, and iodide, those are all conjugate bases of strong acids, HCl, HBr, and HI. Therefore, they're all good leaving groups. This is something that I touched on with you in chapter 6. So if the halogen acts as a leaving group, and for the substrate to undergo elimination or substitution reaction, it's got to possess a good leaving group. So there's another reason why alkyl halides undergo substitution and elimination reactions. They're really set up for it. Well, I told you that in chapter 6, we touched on what a good leaving group is. Well, let's dig in a little bit deeper on leaving groups. And this slide gives you an actual table where it shows you all the good leaving groups that you need to know in Chemistry 3101, at least for chapter 7. Later on, we'll see some other ones, but for now, these are the ones that we're going to be concerned with. So a good leaving group is the conjugate base of a strong acid. Think about it. What is the conjugate base of a strong acid? Do you remember, if you have a strong acid, its conjugate base is going to be really weak. Well, if you think about a base as being a weak base, that means it doesn't want to grab protons. It's very happy the way it is. So if you have the conjugate base of a strong acid, like iodide, bromide, chloride, or water, those are all very happy the way they are, right? Water doesn't going around being like, give me a proton, I need proton. Water is very content the way it is. It's a stable base, much like iodide, bromide, and chloride are. That's why they make such good leaving groups. They're happy when they leave. They're totally fine with it. Now you're probably saying, what is this thing right here? That's another leaving group. You didn't mention that one, Mr. Dion. Well, let me introduce you to a new strong acid. It's shown over here. This acid has kind of a longish name. I'll show you what it is. It's called toluene sulfonic acid. And actually, correctly, it's called para-toluene. So we'll call it para-toluene. And chemists love acronyms almost as much as the military. And so for para-toluene sulfonic acid, sometimes we just call it PTSA. We'll call it, or PTSA. So PTSA, you can see, is a very strong acid. It's got a pK of -3. It's even stronger than hydronium. Ergo, once it donates a proton, its conjugate base is a weak base, and therefore it is a good leaving group. So this is just the conjugate base of para-toluene sulfonic acid. We call this a tosylate. Tosylate. Right? So there's a new leaving group, just one. Everybody knows iodide, bromide, chloride, and water, and now you throw tosylate into the mixture, and those are the 5 leaving groups that you're going to be seeing in this chapter. Again, they're all the conjugate bases of strong acids. All of these acids, here's my highlighter, all of these acids are strong. Once you get down to HF, HF is not a strong acid. It's not a strong acid, therefore fluoride is not a good leaving group. The conjugate base of water is hydroxide. That's not a good leaving group. Neither are these alkoxides for the same reason, and an amide is a poor leaving group too. So again, to review, the conjugate base of a strong acid is a weak base, and a weak base is a good leaving group. So you can either try to memorize them, but I think the best way to know it is just concentrate on what the strong acids are and say, if these lose a proton, what's left over is a great leaving group. Give me a thumbs up if you follow me on that one. Any questions about that? Okay, cool, yeah. And again, if you're thinking, oh, shoot, there's another thing for me to memorize, oh, fiddlesticks, remember, by the time you finished going through all the practice problems in Chapter 7, you're going to have these down pat. You're going to know that when you see a tosylate, it's a good leaving group because you will have seen it enough times. Okay, so we finished section 7.1, which is kind of an introduction to substitution and elimination. Why can alkyl halides undergo substitution and elimination? It's because some reactants can behave like a hydroxide, could be a base. It can behave as a nucleophile depending on the situation. We can get mixtures. We talked about what a leaving group is. If you go to the title of this chapter, it mentions alkyl halides, and something that we haven't done yet is talk about how to name alkyl halides. And so now we're going to cover alkyl halide nomenclature. And I got some great news for you. If you spent a lot of time learning how to name alkanes and you said, oh, Mr. Dion, I spent a lot of time memorizing methyl, ethyl, propyl, isopropyl, tert-butyl, sec-butyl, isobutyl, all that stuff. If you spent a chunk of time on that, well, I have some great news for you. All of those rules that you would have learned in there, all of that nomenclature can be applied in this section. So great news. It even refers to it right here in the slide. It says, recall from section 4.2 the steps that we use to name a molecule. The only difference is that now we're going to have a halogen, right? If we have a fluorine, right? If we have a fluorine, we use the prefix fluoro, or we call it a fluoro as a substituent. If we have a chlorine as a substituent, we call it a chloro. If you have a bromine, you can guess, you call it a bromo. And then if you have an iodine, we call that an iodo. Iodo. All right, so what are we going to do? We're going to identify and name the parent chain. We name the substituents, methyl, ethyl, propyl, chloro, iodo, bromo, whatever. We're going to assign a locant or a number to each of the substituents, and we put it all together in alphabetical order, and that's it. Nothing more than that, my friends. Take a look at these examples and convince yourself that they're numbered in the most appropriate way. I mean, in this first compound, we're looking for the longest carbon chain. We see that it's 1, 2, 3 carbons. And I mean, you could have gone in this direction too, 1, 2, 3. Since there's a plane of symmetry here, either way, you end up with the same thing. You would call this molecule 2-chloropropane. The next one, the longest carbon chain, contains 5 carbons. We start numbering from the left because that gives the substituents, the methyl and the bromo, the lowest possible locant numbers. If you had started numbering over here, instead of a 2, they would have been a 1, 2, 3, 4. 2 is lower than a 4, therefore the way it's numbered is correct. So we have 2-bromo, 2-methylpentane. Why do we put the bromo first? Again, we're just using alphabetical order, right? A to Z, and the B comes before the M. And in the next one, we even have a stereocenter. Ooh, we should check that stereocenter to see if it's correct. Let's get a little Chapter 5 practice. Let's see here. I'm going to go a little bit quicker than I did in Chapter 5. So look, the bromine is number 1. The hydrogen is number 4. All of this is number 2. And all of this is number 3. So we go from 1 to 2 to 3. It's clockwise, therefore it's R. This looks good to me. So whoever labeled that was correct. But we have R5-bromo 2,3,3 trimethyl heptane. Why do we name it in such a way? Well, we want to give the first substituent the lowest possible number. That's why we start over here. If we had started on the right-hand side, the first substituent would be the bromine, and it would have been at 1, 2, 3. Since a 2 is lower than a 3, done. We start numbering from the left. Any questions about that? And again, never hesitate to interrupt me if you have a question about anything. I'm more than happy to answer it. Oops. All right. Well, with that in mind, let's take a look at systematic versus common names. So we have systematic names for alkyl halides, and then we also have what are called common names, and both of them work. Okay, and I'll actually mix them up. I'll use both depending on the situation. When I use common names, it's going to be for very simple alkyl halides. So something that's very simple or small, or that's got some kind of alkyl group that's just easy for us to come up with a name. So let's see here. Some simple molecules are recognized by their common name. We just give the name of the alkyl group, and then we name the halogen. For example, if you have an ethyl group and a chlorine on it, you'd call it ethyl chloride. Let's imagine you had, a methyl group with an iodine on it. You'd call it methyl iodide, so on and so forth. I think I told you the other day that if you have a CH2 group, a CH2 group is called a methylene. So if you had CH2 with 2 chlorines on it, you'd call it methylene chloride. Whereas the systematic name is where we name the compound as a haloalkane. So we list the halogen first. So if you have a chlorine on an ethyl, you'd call it chloroethane, right? If you have 2 chlorines on a methylene, you'd call it dichloromethane, so on and so forth. So what we want to try to do is give reasonable names for these 2 compounds. Well, the first thing I'll tell you is this, is that we cannot give either of these common names because there's no alkyl group that you could just look at and identify immediately in either of these. Impossible. So if we find the longest carbon chain in the one on the left, we see that it has a total of 4 carbons in it. So we go 1, 2, 3, 4 like this. If I highlight this carbon in yellow, and if I highlight this carbon in red, could anybody tell me which carbon would you start numbering on? Would you start at the yellow carbon or the red carbon? Keeping in mind that our chain has all 4 of these carbons. I'm trying to highlight it in green. Would I start on the yellow one or the red one? Does anybody have an idea? Absolutely. Yes, I'd start on the yellow one, right? Because if I start on the yellow one, then my locants will be, if I start here, 1, 2, 3, 4, then I have 2, 2, 3 for my substituents. Whereas if I went the other way, I'd have 2, 3, 3. This is my tiebreaker. And so the way that I have it labeled is the correct way. If we put all this together, we've got a 2-bromo, a 2-iodo, and a 2-methyl. And so the 2-bromo is going to come first, the 2-iodo will be second, and the 2-methyl will be third. Let's scribble that down. We've got 2-bromo, 2-iodo, 3-methylbutane, 3-methylbutane. Again, the longest carbon chain, right? The butane is these 1, 2, 3, 4, like this, so butane. Okay, and next what we got to do is we have to assign stereochemical configuration to this stereocenter. Now here's a little trick, because our lowest priority group, our highest priority group is the iodine, because iodine has the highest atomic number out of everything in here. It's element number 53. Then the bromine is number 2. This is a methyl group, so it is last place. So we're going to put a number 4 here, and then you have an isopropyl over here, so that's going to be 3rd place. Now, the lowest priority group is going down. It's not in back. And so what we want to do is we want to imagine that we're standing on top of this molecule and we're looking down here, right? Because then the lowest group would be behind us. What would we see? We would see something that looks like this, where if you're going clockwise, you'd see a bromine, then you'd see you'd see a bromine, then you'd see an iodine. I got something against this iodine. You get a bromine, then you get an iodine. then you have an isopropyl like this. And so how are you going to be going? You're going to be going 1 to 2 to 3, which is counterclockwise. And so the stereochemical designation would be S. And we'll put that in here, that this is S, 2-bromo, 2-iodo, 3-methylbutane. Why is only the bromo capitalized? I don't know. I just put a capital letter in there. You don't need to at all. You can leave that as a lowercase letter like that. All right. Is everybody with me on the stereochemical designation of that one? Looking down that bond. This is where handheld models can come in really handy. You know, if you're struggling with visualizing something that's just on a piece of paper and thinking about it or imagining it in 3D in your brain, it's like I told you in the stereochemistry chapter, it's a skill that can be learned, but it's definitely challenging. All right. The next one, well, the next one, it doesn't matter which way we go. And if you've been looking at it already, we have 1, 2, 3, 4, 5, 6 carbons. And the reason why you would start numbering here 1, 2, 3, 4, 5, 6, because you might be saying, well, Mr. Dion, if you numbered here 1, 2, 3, 4, 5, 6, I'm going to have substituents at 2, 3, 4, and 5. And the way you've numbered it in red, I have substituents at 2, 3, 4, and 5. Well, if you end up with a tie like that, what do you use to solve it? You'd go with alphabetical order. So if you have a 2-methyl versus a 2-chloro, chloro is going to come first because C comes before M in the alphabet. So we've got a 2,3-dichloro, 4-isopropyl, 5-methyl hexane. So I'm going to scribble that down. I don't have a lot of room, so I'll put it here. Let's see here, 2,3-dichloro. What's next? I have a 4-isopropyl, and then a 5-methyl hexane. I knew I was going to run out of room. There we go. And we have 2 stereocenters in this molecule, don't we? We have a stereocenter at carbons 2 and 3. Let's see if we can assign their stereochemical configuration. So we'll start with number 2. So this one here, we've got our hydrogen going in the back. That's good. The hydrogen is lowest priority. The chlorine is first priority. This is second. This is third. We go from 1 to 2 to 3. So it's 2R. Scribble that in here. So we've got 2R and then 3 something. So there we go. Now let's figure out the stereochemical configuration of the third carbon. I'm going to erase all this. Do that. We'll put this hydrogen going in the back. We've got the chlorine is 1. The hydrogen is 4. This is going to be 2. This will be 3. So we're going from 1 to 2 to 3. This is also R. So we've got 2R and 3R. So let's put that in here. 2R, 3R, 2,3-dichloro, 4-isopropyl, 5-methylbenzene. Is that a lot or what? That's a mouthful, that one. And that's a lot of work to name something that's just a simple compound. Give me a thumbs up if you follow me on that. Any questions about those 2 compounds? No? Okay. See, you can see how organic chemistry loves to dredge up, old concepts. I mean, not that old. We studied stereochemistry a couple of weeks ago, maybe last week. But, you see how you always have to be on your toes with those things. Even in organic chemistry, too, they'll ask you to name a compound, and it's always going to have a stereocenter in it, so you got to get some practice on that. Well, we're going to get some more alkyl halide nomenclature practice in just a second, but I want to cover a couple more things with you here. I mentioned this whole Greek letter thing to you, that the carbon that's attached directly to the halogen, we call that the alpha carbon. So you can imagine if you go out from there, then you get a beta carbon, then attached to the beta carbon, you have the gamma carbon. If you kept going from there, you'd have what? The delta carbon. And after that, I wouldn't worry beyond that. So there we go. Now, substitution reactions only occur at the alpha carbon. Why is that? It's because the alpha carbon is electrophilic. The beta carbon isn't electrophilic. If we look at this compound, why is this carbon an electrophile? Again, it's because you have a dipole going this way, which renders this carbon partially positive. The beta carbon, the delta carbon, the gamma carbon, those are too far away. They don't feel that electron withdrawing effect. Something else about these whole substitution reactions here, it says the amount of branching at the alpha carbon affects the reaction mechanism as to whether we have substitution or elimination. And there's three types of alkyl halides. Look at the alpha carbons here. If the alpha carbon has one R group attached to it, we call that a primary alkyl halide. If the alpha carbon has two R groups, we call it a secondary alkyl halide. And if the alpha carbon has three alkyl groups attached to it, we call it a tertiary alkyl halide. You really need to know the difference between a primary and a secondary and a tertiary alkyl halide, because it has a severe consequence when we look at substitution and elimination reactions. For example, later on we're going to learn that primary alkyl halides mainly undergo substitution, whereas tertiary alkyl halides mainly undergo elimination. And then we have secondaries, which are somewhere in the middle. Right? They can undergo substitution and elimination. If you've been wondering, where would I find an alkyl halide in my everyday life? Well, it depends on what you do in your everyday life, I suppose. But some alkyl halides are actually used as insecticides. If you take a look at these ones here, we have DDT. And DDT was used to kill mosquitoes, and they used it in Africa, and they used it in North America as well, but they used it in Africa even longer. And what's cool about DDT is that it saved so many human lives because it cut down on malaria in places where malaria is a problem. But then they found out that it was, deleterious to the environment, and so it's been outlawed in a lot of places. And then you have lindane. Lindane is used as an insecticide in some shampoos to remove head lice. So yeah, that's what it's used for. Lindane is kind of like a, last resort as far as my understanding is. I think it's hard on the scalp, and it might be even slightly poisonous. I'm not exactly sure. But so these are both insecticides, so that's where you'd find some. For each of these, it says here, label each halide circled as primary, secondary, or tertiary. For the circle ones, label all the alpha, beta, gamma, and delta carbons. Well, if you look at DDT, this would be the alpha carbon, this would be a beta carbon, this would be a gamma carbon, this would also be a gamma, this would be a gamma carbon here, this would be a delta carbon, this would be delta, this would be delta, this would be delta. So that's labeling all of those. And it says label each halide as primary, secondary, or tertiary. If we look at the alpha carbon for DDT, so let me just highlight that one here, it's attached to only one carbon, and therefore this would be primary alkyl halide. These are not alkyl halides, these are aryl halides, so we're not going to worry about those right now. If we go over to lindane, you can see that every one of these chlorines has an alpha carbon attached to it. I'll just pick one of them. So we have an alpha carbon, this would be the beta carbon, this would be the gamma carbon, keep going, and then this would be a delta carbon. So they share this delta carbon. And what kind of alkyl halide would this be? The alpha carbon that I have the black line drawn to, would this be primary, secondary, or tertiary alkyl halide? Can anybody tell me? Exactly, it's secondary. Somebody asked me, how do you know if it's alpha or beta or gamma or delta? All I'm talking about is just looking at this specific carbon. I just picked this one that I have highlighted in yellow. The carbon that is attached directly to this halogen is called the alpha carbon. As you keep going away from the alpha carbon, the next one would be beta. After beta comes gamma. After that comes delta. All right, there we go. And, looking at that, you might think, well, jeepers, it looks to me like alkyl halides are just a bunch of poisons, insecticides. But halides appear in a whole bunch of different natural products as well. They're actually found in antidepressants. If you've ever heard of Prozac, you could look up the structure of Prozac. I can't remember if I have it in a slide coming up, but Prozac has fluorine in it, which is kind of interesting. Or antimicrobials like Bronopol has bromine in it. Splenda, for example, has a halogen in it, has chlorine in it. So that's kind of interesting there. Anyhow, I'll leave that as an FYI, but let's move on and let's try naming some more compounds here. So it says assign a systematic name for each of the following. We've got a 7.1b. What's our main carbon chain here? It's got 1, 2, 3, 4, 5, 6 carbons in it. So this is some kind of cyclohexane. We could put that down. We have cyclohexane. And then if we number, we have 1, 2, 3, 4, 5, 6. So we have both of our substituents at carbon number 1. So we would call this 1-bromo, 1-methyl cyclohexane. Why do we put the bromo first? Because B comes before M in the alphabet. So we've got 1-bromo, 1-methyl cyclohexane. Like that. Now, if you're wondering, well, why do you have to put a locant on there? Well, if you just had 1 bromine on the ring, would you call this 1-bromo cyclohexane? No, you would just call this bromo cyclohexane. If you were to put a 1 there, that would be redundant. Since there's only one substituent, whatever carbon the bromine is on, we just assume that's the first carbon. However, once you have 2 substituents, then you have to provide a locant. Why? Well, let's imagine we have a different compound that's got a bromine and a methyl on it. But let's imagine you have the bromine here and the methyl down here. Right? Then you'd have to call that 1-bromo, 2-methyl cyclohexane. So 1-bromo, 2-methyl cyclohexane. All right, so we start to use locants when we have more than one substituent on our ring. What about the next one? Was anybody able to assign the stereochemistry to this one? Could anybody tell me if this stereocenter here is R or S? I'll give you a second to think about it. All right, I got 2 people who say R. Let's give it a shot. So what do we got here? We got the chlorine. That's the highest priority. We have the ethyl, which is the lowest priority, and it's in the back. Why did I give it the number 2? I don't know. So 1, 4. There we go. We have the propyl, which is 2, and we have the propyl would be 3, and we have the butyl, which would be 2. That's a lot better. So we're going like this. Perfect. Both of my students got it 100% correct. The stereochemistry here is R. So I'm just going to pencil that in here so I don't forget it. This is R. Our longest carbon chain is 1, 2, 3, 4, 5, 6, 7, 8 carbons. So this is some kind of octane. We've got 1, 2, 3, 4. So we've got a 4-chloro, 4-ethyl octane, and then it is R. So let me just zoom out here and let's write this whole thing down. So we've got R, 4-chloro, 4-ethyl octane, just like that. Good. And then the last one, let's just do this one a little bit quicker. We've got 1, 2, 3, 4, 5, 6. So this is some kind of hexane. We've got a 5-fluoro, 2,2-dimethyl hexane. So we've got 5-fluoro, 2,2 dimethylhexane. And we need to assign a stereochemistry, so let's zoom in here. Our hydrogen is going in the back, like this, good. We've got our highest priority group, we've got our lowest priority group, we've got second highest and third highest, so we're going from 1 to 2 to 3, which is clockwise, and so the stereochemistry here is R, so we'll put that in here, R, 5-fluoro-2,2-dimethylhexane. And there you have it, my friends. Well, that brings us to section 7.3, which deals with substitution reactions and concerted substitution reactions. And you might remember that I actually mentioned the word concerted earlier in this lecture. And it says here that a substitution reaction where a nucleophile displaces a leaving group involves two steps, right? We have a loss of a leaving group and we have a nucleophilic attack. However, there's two possible mechanisms. There's a concerted one. That's where everything happens at the same time. You have the nucleophilic attack and the loss of leaving group occurring simultaneously. And then we have stepwise. This is where we have the loss of leaving group first, and then we have the nucleophilic attack. Check this out. It says the concerted mechanism involves the breaking of the bond to the leaving group and the making of the bond to the nucleophile at the exact same time. Check it out. If you look in here, this curved arrow represents the nucleophilic attack, but simultaneously, we have the loss of leaving group. You notice something about this alkyl halide? Could anybody tell me, is this alkyl halide shown on this slide, is this primary, secondary, or tertiary? Not a trick question. Absolutely, yeah. Yeah, so notice that this is a primary alkyl halide. I think that's kind of interesting, considering I told you that primary, secondary, and tertiary alkyl halides will have different reactivities when we're looking at substitution and elimination. Well, let's move on from there. In the stepwise mechanism, the leaving group leaves first, and then we produce a carbocation, which is followed by a nucleophilic attack. So check it out. Now we have a tertiary alkyl halide. The leaving group just leaves. You make a carbocation, which is a really powerful electrophile. So now the nucleophile can just come in and attack it. So loss of leaving group followed by nucleophilic attack, stepwise mechanism. And we're going to go over this in even more detail in section 7.8, the stepwise mechanism. Well, let's get back into that concerted mechanism. And the concerted mechanism, we call it an SN2 reaction. It says here, what does SN2 stand for? Well, I can tell you the S stands for substitution. So substitution. The N stands for nucleophilic, and the 2 stands for bimolecular. You might be sitting there thinking, Mr. Dion, you lost me at bimolecular. Well, all it means is that reaction is second order. So the reaction is second order. And hopefully you'll remember from rate laws, we can have first order reactions, second order, and third order, so on and so forth. So this is a second order reaction. I want me to tell you a great mnemonic that my students taught me years ago, which was, they said, this is how we remember it, Mr. Dion. SN and the 2 stands for together, meaning the nucleophilic attack and the loss of leaving group, they occur together at the same time, and that means it's a concerted reaction. So we have our nucleophile attacking our electrophile, we have the leaving group leaving, and we end up with a new compound, and our leaving group has left. So how would you write a rate law for this reaction if it's a second order reaction? Well, the way that you would do that is you would say the rate is equal to the rate constant K multiplied by the concentration of the nucleophile, or nucleophile, multiplied by the concentration of our substrate, our alkyl halide. So I'll just write down they have here in this specific example, right? Because a bimolecular reaction or a second order reaction means it's going to depend on the concentration of both the nucleophile and the substrate. Now, what about the stereochemistry? What if our electrophilic carbon is a stereocenter? Well, in that case, we can actually see that the stereochemistry changes. The stereochemistry that we're starting with in our substrate dictates what the stereochemistry of our product is going to be. Check it out. If we start out with a stereocenter that's S, after we have our nucleophilic attack and loss of leaving group, and you could practice drawing the curved arrows, here's our nucleophilic attack, here's our loss of leaving group, we invert the stereochemistry from S to R. And we call this, or sometimes students will describe this as like an umbrella flipping in the wind. They'll call it a flip. And if I go over to my camera here, and this is just my best way of showing you, it's kind of talking with my hands, but I figure, what, it's worth a try. If you imagine that, this is your electrophilic carbon. If your electrophilic carbon is here, what happens is when the nucleophile comes in, it causes the stereocenter to invert like an umbrella flipping in the wind. So all the substituents are going this way. Then after the nucleophile attacks and the leaving group leaves, it inverts, and I can't invert my hand. Sorry, I'm not double jointed. But does that make some sense? You attack, and then the bonds are going on one side, and then they go to the other side. And so you're inverting the stereochemistry like an umbrella flipping in the wind. Is anybody with me on that? Okay, cool. Yeah, just the idea of the umbrella flip. Now, if you just want to memorize it, that will work too. But I just thought I'd kind of show you a little brief demo of what the heck is going on there, at least to the best of my ability. So we call that inversion of configuration. I'll scribble that down here for you. We call inversion of configuration. So if we have an R stereocenter, it's going to become S, and if you have an S stereocenter, it's going to become R. Now, why do we get that happening? Why? Because if you're thinking, well, Mr. Dion, the only reason that it flips like an umbrella in the wind is because the nucleophile is attacking from this side. If the nucleophile could attack from this side here, which it can't, but if it could attack from that side of the molecule, then you wouldn't invert the stereochemistry. Well, there's a good reason why it does this backside attack. Now, there's a couple reasons given in our textbook. One of them has to do with MO theory, which is shown on this slide here. You don't have to worry about MO theory at all. I'm not going to ask you anything about MO theory. What I think is an easier way to remember why the nucleophile attacks from the backside deals with the electron density of the halogen itself. So let me show you. If I zoom in here, okay, on this step, the nucleophilic attack, why does the sulfur, why does it attack from the back like this? Why does it not attack from the front like this? Well, if you think about it, you get a big old bromine here, which has got a bunch of lone pairs on it, and then you have a negative charge on your hydrosulfide ion. So this thing doesn't want to attack from the front side, because then, draw with just a regular pen here, it doesn't want to do this because then the negative charge has to get too close to all the electrons, which aren't even bonded on this halogen. And that is why I think it's the easiest explanation for why the nucleophile attacks from the back side of the molecule. If you want to read the whole section about the molecular orbitals and why that happens, it's because it doesn't encounter a node, go ahead and do that, but I will not be asking you any questions about MO theory with respect to backside attack. So what if we wanted to draw a transition state? If you remember in chapter 6, we talked about transition states, which are where bonds are simultaneously being broken and bonds are being formed. Well, I can tell you right now, I am never going to ask you to draw a transition state on a quiz in Organic Chemistry 1. If you take Organic Chemistry 2 with me, I'll never ask it to you on a quiz. However, I will assign problems from the book or tell you to try problems from the book where they ask you to draw transition states. Why? Because I think it's a good practice to learn how to draw them so that you understand very clearly that bonds are being broken and bonds are being formed. So check this out. We have this substitution reaction. Here's our hydrosulfide. It's doing the backside attack on this molecule. We're getting this hydrogen bond going over here. The methyl's coming over here. The ethyl's coming on this side, so that we end up with the S stereochemistry for our product, our thiol. So what does the transition state look like exactly? Well, let's try to draw what it's going to look like. We're going to have this bond being formed, and we're going to have this bond being broken simultaneously. So let's see how we could represent that. Here's how I would do it. I would draw the electrophilic center, which is this carbon here. I'm just going to pencil it in. We're going to have our methyl group going straight up. We've got our hydrogen in the back like this, and then we have our bromine going straight down, and we can, sorry, our ethyl group rather, my mistake, the ethyl group going straight down, and we can draw a dashed line to the bromine as it's breaking, and we can draw a dashed line to the hydrosulfide as that is the bond that's being formed. Now the hydrosulfide is negatively charged, but it's going to lose some of that negative charge, so I'll put a partial negative charge. And the bromide isn't fully negative yet, but it's becoming more and more negative, and so I'll put a negative here, a partial negative. And this double dagger here that kind of looks like a telephone pole, whenever you have something like this outside of a square bracket, that is the symbol for a transition state. It's just a convention in organic chemistry, in any kind of chemistry, for a transition state. So that's what the transition state would look like. But the bottom line is when you have inversion of configuration, if you're starting with something that your electrophilic center has a dash on it, after the SN2 reaction, it's going to become a wedge. If you're starting with a wedge, after your SN2, it's going to become a dash. So let's try a practice problem that represents the backside attack. It says, draw the product for this reaction. We have S2-chloropentane in sodium hydrosulfide. So let's start by drawing 2-chloropentane or S2-chloropentane. So we have 1, 2, 3, 4, 5. If you're wondering, hey, Mr. Dan, how do you draw S2-chloropentane? Like, how do you know whether to put it on a dash or a wedge? Here's my answer. What I do is this. I think the easiest way to do it is just to put it on a dash and then check the stereochemistry. If it's R, then you just shade it in. You just color it in, and there you go. Then it would be S, okay? That's just my fast way of doing it. So let's take a look here. If we have the hydrogen coming out in front, this would be 1, this would be 4, this would be 2, this would be 3. You're going clockwise, which is R. It's counterclockwise because the hydrogen is coming in front. Therefore, this is S2-chloropentane. So there's nothing wrong with this compound. It's perfectly good. And now we're going to treat it with the hydrosulfide ion. I'm going to leave the spectator ion, the sodium, out. I'm not really worried about that. So this is my nucleophile. They're telling me it's an SN2 reaction. That means it's together. My nucleophilic attack and loss of leaving group will occur together or in a concerted fashion. And where's my electrophilic carbon? It's the carbon that the chlorine is attached to. So I draw a curved arrow from a pair of electrons on my nucleophile to my electrophilic carbon, but carbon cannot have 5 bonds. But lo and behold, I've got a good leaving group. So my leaving group is going to leave like this. Now remember, this is a stereocenter, and what's going to happen is my S stereochemistry is going to become R. And so what I'm going to do is I'm going to convert my dash into a wedge when I draw the bond to the sulfur. Let's draw the 5 carbons, 1, 2, 3, 4, 5. And now we have a wedge going up here, and we have our thiol like that. So this represents the inversion of configuration. Inversion of configuration. Like an umbrella flipping in the wind. Give me a thumbs up if you follow me on that. SN2 reaction. So SN2 was substitution. N is nucleophilic. And 2 means bimolecular. Or second order. Just a second order reaction. Therefore, if we were to write a rate law for this reaction, we would say the rate is equal to K, the rate constant, multiplied by the concentration of our S2-chloropentane, so this, and the NaSH. It depends on the concentration of both of them. I was just checking my notes to see if there's a question that I wanted to ask you, but let me just ask you very quickly, and you can either unmute your mic and yell me the answer, or you can type it in the chat. But let's just say, right, this is our rate law, okay, for this reaction that's on this slide. What would happen to the rate if I doubled the concentration of the alkyl halide? How much would the rate go up if you doubled that concentration? And it's not a trick. The answer is as simple as you think it is. Exactly. It would double, right? So same rationale. If you doubled the concentration of NaSH, it would double the rate. Okay, let me ask you one more question. If you doubled the rate of this and you doubled the rate of this, the nucleophile and the substrate, what would happen then to the rate? You doubled both of them. How much would the rate go up? Exactly. It would go up by a factor of 4, right? So your rate, you'd have rate is equal to K times twice as much and twice as much. So then you'd be multiplying the rate constant by 4, so it would go up quadruple. Thanks, Nicole and Angel, everybody. You're all 100% correct. Pretty neat, huh? Anyhow, so that covers SN2 reactions and just how we do the inversion of configuration. Well, next what we want to do is we want to really do some deep diving into SN2 reactions and talk about the rate of SN2 reactions. How do I know my SN2 reaction is going to be fast or slow, or whether my alkyl halide is even going to react in an SN2 fashion? And I think we should take a short break before we get into that.